All right. So we'll see if anybody joins us partway through today. So welcome to our, we'll do one next week for the FRQs, but welcome to our last kind of review session going over all of the fundamental content of the class. We're going to start with simple harmonic motion, which I know we talked about in class, but I want to make sure that we get a chance to talk about it here as well, in case anybody needs to go back, or just in case people were out of class for AP exams. So our framework's going to be very similar to the other review videos. We're going to identify some key relationships and equations, derive some stuff that's not on your formula sheet, and more or less figure out when is simple harmonic motion the right way to look at a question versus kinematics or something else. And we'll also take a look at a few off the review packet. So simple harmonic motion is all about oscillations. It's all about things bouncing back and forth and repeating their motion. The two most common things we see are objects on springs. Ooh, that's fun. And pendulums. My pen is leaking a little bit. That'll be fun. Springs and pendulum. Any kind of thing, though, could be simple harmonic motion if it repeats the motion precisely over a certain time period. The big thing about simple harmonic motion, though, that we want to keep in mind is the total energy, right? Your potential plus your kinetic is conserved. You have the same amount of total energy in the system at all times. And really, that conservation of energy approach is really, really important to understanding the motion of our thing. And the other thing to realize is that this conservation of energy is attached to the idea that simple harmonic motion is always sinusoidal. It's always sines and cosines. So let's say I have some object, and I don't necessarily know whether it's a spring or a pendulum or whatever. I have some object that's moving in this sinusoidal fashion as a function of time. And what I'm interested in is relating that to its energy. Well, right at t equals 0, right when I start, what I notice is that this is at its maximum displacement, what we call maximum amplitude. And if you look at the slope of the graph here is temporarily totally flat. This represents us being at the far end of our motion, maybe for a pendulum, maybe for a spring. And what we'll notice here is at this point, all our energy is potential. That is, we have no velocity, right? We're motionless. And so that's going to correspond to, and okay, this is not a perfect graph that I stole from the internet. That's going to correspond to this point on our potential energy graph, where we are all potential and no kinetic. Well, as I start to move and come back towards a position of 0, I lose potential energy. And as I lose potential energy, I gain kinetic energy because my total has to be the same. So here's my kinetic energy curve, okay, and you in red. And I'm going to hit this point right in the middle, my equilibrium position, is what we call it, equilibrium. We're starting to speed up, speed up, speed up, speed up. And now I'm going to slow down, slow down, slow down, slow down. This is where our energy, here we are already in equilibrium, where our energy is all kinetic, no potential. All kinetic and no potential. So this is also, by the way, the position where we get our maximum velocity. We then start to come to the other side. Our kinetic energy goes down, we slow down, we gain potential energy until we hit at our other amplitude. Down here, minus A. We hit, again, a point where we're stopped, where our velocity is 0, and we are all potential. This quadratic curve here, and it is quadratic, it is in fact a parabola, because if you think about a spring, this is going to be 1/2 kx squared, it's going to look like a parabola. These graph shapes are something that come up from time to time. that the potential energy is a parabola and the kinetic energy as a result is an upside down parabola. It's going to be, you know, kind of some constant total minus 1/2 kx squared for a spring. And so you'll end up with an upside down parabola. And they do ask you to sketch that from time to time. Speaking of sketches, I think it's worth taking a moment to sketch a velocity graph, which is A, a thing they'll sometimes ask you to do, and B, a useful thing to be able to do. And we're just going to go ahead and set on this graph, right? Here's our maximum velocity, whatever it is, positive and negative. And let's take a moment and reflect that at time equals 0, I have no velocity, right? I'm starting from rest. And then I have these other points where I'm at equilibrium and my velocity is a maximum. And then I'm going to stop again. And then my velocity is a maximum. Oh, I skipped a step here. That's okay. I'll come back around to get that. The step that I skipped is, why does my velocity become negative? Well, notice my position starts out positive, and I'm coming back. I'm coming from a positive position for 0. I got a negative slope on my position graph. So I get a negative velocity, comes back to 0, and then a positive velocity comes back to 0, negative velocity. And you'll notice my sine, or my velocity graph is also sinusoidal. In fact, specifically here, my position graph looks like a cosine graph, and my velocity graph looks like a negative sine graph, which, for those of you doing calculus, you will appreciate as being the correct relationship that I have here. So all the graphs are sinusoidal. If I graph acceleration, it would be sinusoidal. So everything about simple harmonic motion is motion in sines and cosines. All right. They do give you a bunch of these equations that are useful. They remind you that it's sine and cosine. They give you kind of a generalized simple harmonic motion position function. They provide you with your potential energies and things. Most importantly, though, they give you the period of a spring and a period of a pendulum. And these are really critical, and you're going to use them all the time. For springs, let's just focus down a little bit on these. For springs, remember that, again, the total energy is constant, same way it is for any simple harmonic oscillator. The easiest way to find the total energy for a spring is if you know the amplitude, because if you stretch that spring out to its maximum extent, the energy is all potential, no kinetic. And so if our amplitude is A, if our maximum stretch is A, well, then it's 1/2 Ka squared is the total energy there. It's important to note, again, for our spring equation, 2 pi root m over k, gravity doesn't come into it, the length of the spring doesn't come into it. The only things that matter to the period are the mass and the k constant of the spring. There is one thing that does change if gravity comes into play. If we hang our system vertically, the period does not change. The period remains exactly the same. However, as we discovered in some of our labs, the system does find a new equilibrium point. You kind of gently let your mass go. It will settle down some distance delta y. And when we say equilibrium point, we mean it. What we mean is that that's the new balance point for the mass. And if you look at the forces on it, well, you'll have mg down, and you'll have that spring force, k delta y, up. And if this thing is truly going to be in equilibrium, they need to be equal. And so what you find is that by hanging our system vertically, the period doesn't change. We just end up shifting our equilibrium down a certain distance, mg over k. There are a few things that we want to be able to calculate here. It's worth noting, right, that our maximum velocity is a root k over m. We've derived that a few times. Let's remember, if you start off with pure potential energy and it turns into pure kinetic energy at equilibrium, that's where we hit our maximum velocity. And so the fastest we're going to get up to is, you can solve that out for v, and we end up with a root k over m. So that's a good thing to either know how to do using conservation of energy or to have in your back pocket. For pendulums, they also give you this equation, 2 pi root L over g. Remember that the big thing that does not matter here is the mass of the pendulum bob. They will try to trick you. At some point, they will be like, oh, what happens if we change the mass? And the answer is, for pendulum, at least, absolutely nothing. Total energy is also conserved for pendulums, but you've got to be a little cautious It's only simple harmonic motion for very small angles, for very small displacements. And in fact, we had to make, way back when, a small angle approximation that our maximum angle had to be within about 15 or 20 degrees in order for this to really be simple harmonic motion. In general, if they give you a pendulum and they want you to find the velocity at the bottom, the best way is actually to use conservation of energy, is to say we start off some distance h above the bottom, we fall some distance h, and that turns into kinetic energy. What's a little tricky here is, what is that distance h? Well, if we look, our total string has a length of L, but this part of it, if we kind of look at our right triangle, this part of it is a distance L cosine theta. And so what we find is that this is L minus L cosine theta, or if you're the kind of person that really likes factoring, you could write this as 2GL 1 minus cosine theta. That's not something that you need to memorize. It's just something you could work out with trig. The maximum velocity for pendulum just being ever so slightly more complicated to do than for a spring. All right. Well, let's ask this question, which is really important. Is how do I know when to do simple harmonic motion? I'm looking at a question on the exam. How do I know it's a simple harmonic motion question? Well, the easiest way to know that it's a simple harmonic motion question is to note that it includes a spring or a pendulum. They're usually going to be pretty clear about whether something is bouncing back and forth. You know, here's a 2018 question, something's attached to a spring and it's bouncing back and forth. A spring or a pendulum bouncing back and forth. The keywords are looking for a period or frequency. Oscillation is a word that just means bouncing back and forth, repeating your motion. So if they mention those things, those are real keys that it's a simple harmonic motion question. Obviously, if they give you a sine or a cosine equation or a graph, it's probably a simple harmonic motion question. You can use some of your pre-cal skills to figure out, what the period of your graph is. The other key is they will sometimes ask you for time in what would usually be an energy question. So let's say, and the example that I used in class, and I think it's a good one, is let's say we have a spring of constant K, and we put a block of mass M on it, and we kind of push this back some distance A, and they're not tied together. We're just kind of launching it, and there's no friction. Well, you could use your simple harmonic motion. You could use your conservation of energy to say how fast the block is going when it comes off the spring. How fast the block is going when it comes off the spring. That's a conservation of energy question. 1/2 K squared is 1/2 mv squared. They might then ask you a weird question, which is, okay, how long does that take? How long does it take from letting go to the block coming off the spring? And that's a hard question to do with kinematics, because with kinematics, like your forces and your acceleration are constantly changing. But what you could say is you could be like, well, okay, if I make a position versus time graph, I'm going to start at some position minus A, and it starts off at rest, and I'm going up to a position 0. And this is basically the first quarter period of my spring, right? That if going from here to 0 is a quarter period, because then I would also have 0 to the other side back to 0, 0 back to where I started. And so the length of time that it's going to take to get from maximum amplitude to 0 is just going to be a quarter of whatever the full period of oscillation was, and you could find that out. So once in a while, they will throw you for a loop and ask for a time question. So if they ask you for time in what looks like an energy question and there's like springs or pendulums involved, it's probably a simple harmonic motion question. Let's take a look at a few of these questions here. One of which is a question that Mr. Bates, that I wrote, and is unnecessarily obnoxious. Number 2 is not the one that's unnecessarily obnoxious. Number 2 is actually, I think, a very nice question. So we're given the mass, and we're given the K value of the spring. So here's our mass, here's our K value. It's allowed to slide freely. At time t equals 0, the spring is stretched a distance of 0.5 meters and released from rest. The next time the mass is at rest is most nearly. So here's the thing. This is a spring question. It asks for a time. Let's go ahead and calculate the period of our spring, 2 pi root m over k. This is 2 pi root 4 over 100. And if I go ahead and calculate the period of the spring, 2 pi root 4 over 100, I get about 1.26 seconds. Awesome. And as a result, because I calculate 1.26 seconds, the answer is B. Why is the answer B? Well, the thing doesn't do a full period, right? We started out on this side. It accelerates towards equilibrium where it gets its max velocity. The next time it's at rest, it's over here at a position of negative A, right? That is not a full cycle. That's only half a cycle. In order to get a full cycle, you got to come back to where you started. So in this case, the answer that they're looking for is actually half the period. So you got to be a little cautious. Often you'll have enough information to calculate the period, but really think closely about those sine and cosine cycles, right? If this is my position and this is my time, think about what they're asking. And in this case, what they're asking is how long does it take to get from here, where again, I'm at rest, to here where I'm at rest. That's only half a cycle. That's not a full period. All right. Number 4 is the aforementioned obnoxious question. And although it is maybe how you would measure the gravity on a planet. So we bring a pendulum of length 1 meter to the planet, and it gives us the period of the pendulum. So the first thing that people wanted to do, which is totally reasonable, is you go 2 pi t equals 2 pi root L over g. And let's see if we can find the acceleration of gravity, little g. So here we're going to go divide by 2 pi. Root L over g. We'll square both sides, which gets us t squared over 4 pi squared equals L over g. Now, if I'm rearranging this, I'm going to multiply g over and then get rid of everything else. So what I'm going to find is I'm going to get g equals 4 pi squared times L. I should be consistent with my symbols. All over t squared. So there's a variety of other ways to calculate it, but this is the most, for me at least, the way that I would like to do it. So 4 pi squared times the length is 1 meter divided by t squared 3.27 squared. Always make sure to use parentheses on your denominator. So I saw this on a lot of people's papers. It's about 3.69, about 3.7 meters per second squared for gravity. And honestly, I should have left it there, but I couldn't leave well enough alone. It asks you for the mass of the planet, and this is where we have to remember the mass of the gravitational acceleration of a planet is big G times the mass of the planet divided by the radius of the planet squared. There's our gravity equation coming in. I can see them doing something like this on an FRQ. And so if I'm calculating the mass of the planet, I'm going to multiply by r squared, and I'm going to divide by big G. So you can always find big G on your formula sheet if you need it. So multiply by 2.44E6 squared divided by big G. And if I've done everything properly, I get about 3.3 times 10 to the 23rd proton. So you can find that one right there. This one's got a 2-step. They would never do this to you on the exam as an actual multiple choice question. They might give you the first half as a multiple choice question. But if they wanted you to do this whole thing, it would be probably an FRQ in length here. And that actually, I think, was mostly what the questions that I wanted to talk about for simple harmonic motion, unless Kai, there were any. I know that I only gave 6 multiple choice questions here, but if there's any other ones that you were stuck on.
Just for energy.
Oh, for energy movement. Okay, we'll take a look at those real quick at the end if you'd like. All right, so moving on, just for simple harmonic motion, remember, you got to think about conservation of energy and those sines and cosines, right? Where in the cycle am I? Is it all potential? Is it all kinetic? Am I at equilibrium? Where am I in the cycle? Because being comfortable with what parts of the cycle you have maximum velocity and what parts of the cycle you're at rest is going to be really, really, really critical. Let's talk about the very last thing here, which is rotation in this case. So this is our last unit, and I think just because of its newness and the pace at which we went through it, the most perplexing. So again, the big message with rotation is that every single rotational equation has a linear one that it's exactly the same as. I mean, more or less, there are a few exceptions, but every rotational equation has a linear analog. So we're going to identify some of those key equations and relationships, look at the moments of inertia or rotational inertias for some common objects, look at torque in Newton's second law, and then ask, when is it rotation? And I will say, this tends to be one of the units where even though the math is a little bit harder, there's less confusion about when you're supposed to use rotation because there's a rotating object, like, or they talk about torque. It tends to be a little bit clearer in that case. So let's start from the beginning. Every rotational equation has a linear analog, and you've got most of them, in fact, on your formula sheet. So instead of distance equals speed times time, right, if you're not accelerating, your angle is omega times time, right? You've got your 3 kinematics equations, all in rotation, although they don't give you the third kinematics equation, the omega final squared equals omega initial squared plus 2 alpha delta theta. But again, you can always make a rotation equation by looking at what the linear equation would be and subbing in, right, omega instead of v, alpha instead of acceleration, and so on and so forth. So rotational kinematics is all obsessed with angles. And the reason that it's all obsessed with angles and angular velocity is, again, because every single point on a wheel has a different velocity, but they all have the same omega. The angular velocity of the wheel is represented by just one number. The most important equation in all of rotation that is not on your formula sheet, by far the most important, is this one, is V equals R omega. This is how you get back and forth. If you've got an object that's rotating and you need a meters per second, a linear velocity, V equals R omega. This is, by the way, why things that are further out have more velocity, even though they have the same omega, because they're at a bigger radius. When it gets to torques and other things, we typically actually need to look at both torque equals I alpha and F equals ma in order to really understand the full motion of an object. You don't always have to look at both, but if you, in general, it's actually quite useful. It's quite useful. For that moment of inertia, we're going to make some comments about that in a moment. An important thing that's on your formula sheet is recognizing that the I of a point mass, right? If I just have a satellite or a bug or a little dot, something whose shape I don't care about, it's I, it's just mr squared, where m is its mass and r is how far from the axis it is. Kevin, you can hear me okay, right? Just check. I just want to check my audio. Yeah, excellent. There's some comments about energy. These are also in your packet. When something is rolling, it's really important to note that it is both rotating and translating. So it has 2 types of energy. It has 1/2 I omega squared and 1/2 mv squared. In that case, it is both spinning and moving. This, by the way, is why some of those objects, when we race them down the ramp, why some of those objects went faster than others, is that the higher your I, the more energy it takes to rotate you. And so the less energy is available for just good old 1/2 mv squared, right? Your rotational kinetic energy takes up a bigger piece of that budget, and you don't actually get to go as fast in this case. Torque is so important. For calculating torques, remember that it is the lever arm times your force. They have to be perpendicular to get any torque done. And this is why they write in your formula sheet. Actually, I think they give it to you as RF sine theta, but that's fine. As the lever arm times the force times the sine of the angle between them. Please be careful on that sign. Just because it says a sign here does not always mean that when you're calculating a torque, sign is what goes into your calculator. Because sometimes the angle that they give you is not the angle that you want. This theta specifically refers to the angle between kind of the radius vector and the force vector. So like for this latter question, if I want to know the torque from gravity, well, I got to be a little careful. I'm given 53 degrees here, but if I use the sine of 53 degrees, I'm actually going to be incorrect. It turns out that what I need to look at is either the perpendicular component of my force, which in this case would actually be given to me, you think about a ramp, by that force times the cosine of 53 degrees. Or, if I don't want to do that, what I need to look at is I need to look at the angle here, which is not 53 degrees, but is in fact, what, 37 degrees? And wouldn't you know it, the sine of 37 degrees turns out to be the same as the cosine of 53 degrees to give you the same answer. So just please be careful that the angle that you're using here is the angle that's intended. Otherwise, what you want is you want the component, you want the trig function that's going to give you the perpendicular component of your force. This torque's like the force and the radius is nice and perpendicular. Remember, by the way, that all of these vectors have weird directions. They have that weird right-hand rule direction. So if I apply a force to this thing, it makes it want to rotate counterclockwise, which is going to give me a torque vector and an angular acceleration vector that are straight up. So remember, the directions of these vectors are a little strange. They use that right-hand rule. Your fingers curl the way that the thing is going to rotate, and your thumb points in the direction of, your torque or your angular acceleration or whatever it is. Angular momentum is the last thing that we talked about, and it's on your equation sheet as L equals I omega. Remember, this is the rotational equivalent of mv, I instead of m, omega instead of v. It does come up, and we showed this the other day, that for a point mass, right, if I've got some axis, and I've got just a little mass going in a straight line, even though it doesn't look like it's rotating, it's just moving in a straight line, it does actually carry some angular momentum about this pivot or about this axis. And if we wait until it kind of comes right here, what we can do is we can actually show that the angular momentum of this thing is just mvr, where again, because this is a rotation, we do want our lever arm and our velocity to be perpendicular in this case. The way that we show this, by the way, is by remembering that the I for a point mass is mr squared, and that the omega, right, if v equals r omega, then omega equals v over r, canceling out one of these, and we end up with m times v times r for a single point mass. And just like regular momentum is conserved, angular momentum is also conserved. Where regular momentum is conserved with no external forces, angular momentum is conserved with no external torques. So if there's no torque on the system, its angular momentum will stay constant. All right. Let's take a look. A couple more things. The I for common objects. So you are sort of expected to know this, but not 100%. It is important to note that the I for a collection of objects is typically just the sum of all the mr squared. So let's say they give us like, a weird little barbell. The rod itself has no mass, but it's got things on the end. Well, what you would do is you would measure the distance to one thing, you'd measure the distance to the other thing, and you'd add up the m times r squareds for the two objects. What comes up more frequently are a variety of different objects like disks or rings or different things like that. You've got this half sheet, the 1/2 mr squared, mr squared, 1/12, 1/3, 2/5, and things like that. It's good to know this, but they will rarely require you to know it for like the purposes of calculation. What they more want you to know is they want you to know which things are bigger and which things are smaller. So knowing, for instance, that a ring has a higher moment of inertia than a disk is an important thing to know. 2/5 is less than 1/2. That's important to know. So what's more common is they'll be like, oh, I'm going to race a solid sphere and a disk down a ramp. Which one's going to win? And you'd be like, oh, well, 2/5 is less than 1/2. So this one has a lower I. If it has a lower I, then more of its energy goes into just regular motion. So the sphere is going to win the race, but it'll be pretty close. So they want you to know which ones are more and which ones are less, rather than knowing specifically what the number is. How do I know when it's rotation? Well, most often it's not that bad. The object is rolling or rotating, or there's a torque or something involved. It involves a torque, angular velocity, angular position, and stuff like that. It also comes up when forces that are applied to an object are off center. So if they draw you a free body diagram and they're like, hey, the forces are here and here, probably that object's going to spin or rotate, right? Unless you're otherwise informed. So, because our free body diagrams don't care about where, like F equals ma doesn't care where the forces get applied, but torque does. All right, let's look at a few of these off the review package that I pulled out at least. For the first one here, we've got a turntable that's initially at rest is set in motion with a constant angular acceleration a, or alpha, sorry. So it starts out at 0 and then starts to accelerate and spin faster and faster and faster. How fast is it going? What's the angular velocity after it's made one complete rotation? So I always like to look at these in terms of what would I do if this were a regular kinematics equation? Right? What if I had an object that was initially at rest and it started to accelerate at some rate a, and I wanted to know how far or how fast it was going after it had gone some distance d. What's the velocity now? Well, notice this is sort of a kinematics question that doesn't involve time, and there's only one kinematics equation that doesn't involve time, which is the third one. The final velocity squared equals the initial velocity squared plus 2 times my acceleration times my displacement. So let's see if we can figure that out. Here we're looking for omega final squared. Well, our initial omega started out at rest is nothing. And it's accelerating to alpha. And instead of my displacement, I'm going to look at my angular displacement. And here's where we got to ask ourselves this question, which is, if the thing goes around one complete revolution, how many radians is that? Well, it's 2 pi radians, right? So if one complete revolution is 2 pi radians, then this ends up being 4 pi times alpha. And then we still got to take a square root. So we end up with c there as our angular velocity at the end of all of that. So again, kinematics equations come in a lot of different forms, and you can use all of them in rotational kinematics. Here we've got a different question. We've got a meter stick pivoted at its center, so the meter stick on its own would balance. We have 2 weights that are having at different positions, and when the meter stick is released from rest, it begins to rotate counterclockwise. And it asks, which of the following statements about the 2 weights is correct? Well, let's take a look. Because what we're going to have here is we're going to have a force MA times G here, and a force MB times G here. And they're at 2 different distances, dA and dB from the pivot. And because these are torques, what we're going to find is that the torque from A, which is its force times distance, should be greater than the other one, because it's rotating counterclockwise. Here's the thing, though. Well, first of all, we can cancel out the G's. It wants us to ask about MA and MB. In this case, I'm going to do this the math way, and then we're just going to explain it. dB divided by dA, which is to say, this ratio dB over dA should be bigger than 1. You know, B is much further out. And so what we're going to find is that MA is actually greater than MB. You don't have to do the equations to think about this. Normally, if the thing we're going to balance, you'd want the big thing close in and the small thing further away in order to balance. If MA is still stronger, despite being closer in, that must mean it's considerably more massive than, because it produces, like it says, a greater torque with a smaller lever arm in this case. All right. What else did I pull out? I pulled out some statics questions. So torque. In this case, we have a rigid uniform rod of mass 6 kilograms and length 1 meter. Note, if it's 6 kilograms, then we're going to end up with a force of gravity of 60 newtons here. It's really, really, really important when you're drawing your free body diagrams for torque that you apply gravity at the center of mass. So this is, if it's a 1 meter, this is going to be, 50 centimeters here, or 0.5 meters away from our pivot. Here's our pivot. And then we've got an upward force of 40 newtons holding the rod in equilibrium. So the first thing that I want to do is let's try to figure out what this distance x is. And if we want our thing to be in equilibrium, we need our torques to balance. So we're going to need 60 newtons times 0.5 meters times 50 centimeters to be equal to 40 newtons times x. So if we solve for x here, that's going to be, let's see, that'll be 30. Half of 60 is 30. 30 divided by 40. So this will be 0.75 meters or 75 centimeters. It's a weaker force, so it has to be further out to get the same amount of force, to get the same amount of torque. Notice, I was nice to you, 75 is not one of the options on here because obnoxiously, and this was a real question, asks how far from the left end of the rod should be applied. Well, if it's 1 meter long and this is 75 centimeters, how far is that? 25. Correct. That's the other bit of it. So, I could have been mean and given 75 as an answer, but I didn't. Would have been unpleasant for me to have done. All right. 7 and 8 we're throwing some people today, which is good. Let's talk about it. We've got a wheel mounted on a fixed frictionless axle, and it's speeding up over time to some final angular speed. And it wants to know what's the average net torque on the wheel. There's 2 ways to think about this, which are really the same. One way is to look at this as torque equals I alpha. And then to realize, well, what is angular acceleration, or at least on average? Because if we want the average torque, we want the average angular acceleration. Our average angular acceleration is just going to be delta omega over delta t. Well, our delta omega, right, this is final minus initial. But our initial is 0, it starts at rest. So our angular acceleration is just omega final over t, which makes this I omega final divided by t. The other way to look at this that gets you to the same place is to think of this actually as an impulse problem. We had fat equals mav as this equation we used before. We do have a rotational equivalent of this. Instead of force, we write torque. Instead of mass, we write I. And instead of this, we write change in omega. And so here we can show, hey, torque is just going to be delta omega over t, and get to the same place, the same philosophy. As for power input to the wheel, let's remember that power is change in energy over change in time. Well, as this thing spins up, it's going to get some rotational kinetic energy. Rotational kinetic energy is, well, 1/2 I omega squared. And how long does it take? Well, it takes t. It takes a certain amount of time t. So it is in fact d here that. And I will note, you could reason that out. A and B are bad choices because they suggest that if it takes more time, then there's more power. Power is energy divided by time. It should require more power if things take a shorter amount of time. The 1/2 I omega squared is just that's our rotational kinetic. All right. Couple more before we close up. Here we've got a diagram at right showing a ladder of mass m and length L. What is the torque due to the weight of the ladder about its contact point with the ground? So here we're asking for the torque from gravity. So we should draw our gravity vector. And the question is, where do we draw the gravity vector on our diagram? And the answer, if you're doing gravity, is always, always, always doing gravity for torque. Always, always, always the center of mass. So the first thing to realize for our torque is that the lever arm is not the full length, right? The lever arm is, well, it's not the full L, it is L over 2. So whatever our answer is, it's going to involve a 1/2. It's going to involve a 1/2. Now the real question here is, all right, I've got my radius, it's L over 2, or 1/2 L, mg. And now the question is it sine theta, or is it cosine theta? Well, and here's where you got to be cautious. They're giving you this angle, but we got to work out what is the perpendicular component of our force, because it's this component that's actually going to generate a torque, right? This component of gravity isn't going to generate any torque. And we might remember from inclined planes that this component is mg cosine theta. Because if this is theta, this is 90 minus theta, which makes that theta again. Which makes that theta again. So in this case, it is in fact 1/2 mgl cosine theta. You got to be a little cautious on that because there will absolutely be cases where it's not just straight up sine. We got to be a little bit cleverer than that. I think I had pulled out a couple more. Oh, those are, that's a physics C question. We'll get rid of that. So let's look at 12 and 13 before we close, and then one more before we close up. We've got a stick pivoted here, and we want to figure out the magnitude of the net torque on the stick. Well, this is really just a matter of doing the math. Notice we don't have to deal with any sines or cosines. Everything is nice and at right angles. So if we're looking at F1, torque 1 is going to be 200 times 0.5 or 100 Newton meters. Torque 2 here, this is going to be 100 Newton meters. Torque 2 here is 100 times 1 meter. This is actually also 100 Newton meters. It's the same exact torque. Half the distance at half the force at twice the distance. We also have a couple torques in the other direction. This one is going to be 50 times 1.5 or 75 Newton meters. And this one here is going to be 25 times 1, 2, 3, 4, 25 times 2 or 50 Newton meters. And then we got to be a little cautious, right? Because we've got 2 that are carrying us in what we consider to be the positive direction, and 2 that are carrying us in what we consider to be the negative direction. So we'll have 200 minus 50 minus 75, so minus 125. So we end up with a net torque of 75 Newton meters in this case. It then asks if the torques applied to the stick for 2 seconds, its angular momentum will be. This is a question of angular impulse, right? If I've got F delta T equals change in momentum, it's actually the case that torque times time is change in angular momentum. So I'm just going to take this and I'm going to multiply it by 2 seconds. Get that. Somebody was looking at this problem at one point and was like, well, there's only 2 answers. Actually, there might only be one answer for which there's only one answer for which there's only one pair of answers that make the answer to 13 twice the answer to 12. No, that's not entirely true. C works also. But still, it's you could try to game it like that. I guess D works also. 3, 650. But you could try to game it out that way. Be like, well, I'm going to have to multiply this by 2, so that's going to help cut down on my answers. Last but not least, we've got number 17. I apologize. This one has a few typos in it. The bullet was intended to be in kilograms, not in grams. And my answers should be in radians per second, not in meters per second. So I'm sorry about that. This is a conservation of angular momentum question, though, because we are causing something to spin through a collision. So our initial angular momentum, remember, for a point mass, this is mvr. So we can go ahead and calculate our initial angular momentum here as 0.02 times 500 times a radius of 0.5. So it starts off with initial angular momentum of just 5. Kilogram meters squared per second is our unit for angular momentum here. That has to be exactly the same as our final angular momentum. And let's just note what our final angular momentum looks like. We have a bullet and a disk rotating together. The I of the disk is 1/2 m r squared. And for the bullet is now rotating around as well. And so remember, it's going to have an I of just little m r squared times omega final. So this is I omega. And note, we've got the I of the disk plus the I of the bullet in this case. We can go ahead and calculate that out. 1.5 squared plus 0.02 times 0.5 squared. So I get a total I here of 0.13 kilogram meters squared equals 5. So I'm going to do 5 divided by that. And I get an omega final of about 38.46 radians per second, which is where I'm at right here, 38.5. All right, I'm going to skip over the strange AP Physics C question. And just note, this is the last of it. Rotation does have a bunch of complexity, but again, the big deal with rotation is that you can use all the intuition you built this year over forces and kinematics and stuff to tell you roughly what should happen. V equals R omega is so critical because it really unlocks a lot of things. This is why we can also do the tangential acceleration of something is R alpha. V equals R omega and its counterpart A equals R alpha. It gets you back and forth between linear and rotational accelerations and velocities, which is just so great. You also have a couple other consequences, right? Our centripetal acceleration is normally V squared over R. If you substitute in V equals R omega, you can find that it's also omega squared times R. So sometimes you have, sometimes depending on what you have, it might be more convenient to calculate your centripetal acceleration that way. So just the thing to do with rotation is stay calm, do the best you can. Mostly, the stuff we've been doing has been very calculation heavy. Most of the rotation on the exam is actually fairly conceptual. So just remember, draw your free body diagrams, calculate your torques carefully, and everything's going to work out just fine. We're going to go over a couple more questions on the side, but otherwise I'm going to close up this video so I can post it later. And let me